be a bivariate continuous random variable with the joint probability density function given by f of x1 x2 is equal to 4x1 x2 e to the power of minus x1 square plus x2 square whenever x1 is greater than 0 less than infinity, x2 is greater than 0 less than infinity, 0 otherwise. So, I hope I have correctly written this for x1 x2 e to the power of x1 square plus 2 0 otherwise x1 is greater. So, because it is continuous random variable, we can take greater than equal to 0 or just strictly greater than 0. Okay, because x1 0 x2 0 this value already is 0. Now, then the transformation it is found, this transformation it is taken, u1 is equal to root over of x1 square plus x2 square. So, u1 is equal to root over of x1 square plus x2 square and u2 is equal to x2, u2 is equal to x2. So, then in the real number, because these are all random variable, this is x1 square plus x2 square and u2 is equal to x2. So, from here we can find u1 square is equal to x1 square plus x2 square and which implies, so now if we want to find the inverse, x2 we are getting nothing but u2, x2 we are getting u2 and so this is the inverse, and if you want to find the x1, so x1 is x1 square we are getting here, from here x1 square is equal to u1 square minus x2 square, where x2 is u2, so u1 square minus u2 square. So, hence we can find the inverse like x1 is nothing but root over of u1 square minus u2 square. So, now we already know the this density function is non-zero in this range. So, x1 is greater than 0 less than infinity and x2 is greater than 0 less than infinity. So, x1 is x2, so which implies u2 has to be greater than 0, x2 is u2 less than infinity. So, in this region range of this transform random variable, and then what about x1, because u1 also x1 square plus x2 square root of u1 if you take, so positive square root, u1 also has to be greater than 0 because you are taking x1 square plus x2 square and less than infinity, and also this relationship root over of u1 square, because it is a square root of something and we are taking x1 that is greater than 0. So, u1 square minus u2 square has to be also u1 square minus u2 square also greater than 0 less than infinity. From here we can get u1 square will be greater than u2 square which is less than infinity, also this is greater than 0. Now, if we consider the square root, because all are positive, so we will take the positive square root. So, then this transform random variable range will be modified to these things. So, this should be 0 to u2 and u1 should be greater than u2 less than infinity. From here we can get u1 has to be greater than 0 less than infinity, because u1 has to be greater than u2. Now, we will find the Jacobian. So, this transformation, what will be the Jacobian? So, Jacobian is defined by this partial derivative del x1 del u1 del x1 del u2, then del x2 del u1 del x2 del u2. So, then you will find this value. So, now you can see that x1 is root over of u1 square minus u2 square. So, del x1, so this is the function component, the inverse of this function u1 u2, it is function of u1 u2. This is also this is h2 u1 u2, but it is just a independent of u1. So, if you want del x1 del u1, so then the differentiation with respect to u1, so then it will be 1 by 2 root over of u1 square minus u2 square, then this is nothing but 2 of u1, again the differentiation of these things, and this is also del x1 del u2. If you do the differentiation with respect to u2, so then again we will find 1 by 2 root over of u1 square minus u2 square. Not only that, again you have to differentiate it, then it will be minus of 2 u2, and then if you do del x2 del u1, del x2 del u1, this will be 0, and del x2 del u2, del x2 del u2, it will be is equal to 1. So then this determinant will be, so we can cancel these things, and this determinant will be nothing but u1 by root over of u1 square minus u2 square. So because in the range this Jacobian will be always greater than 0, because u1 is positive in the range of this random variable. So transform random variable, it is always positive, so that is why it is always greater than 0. Hence we can find the joint probability density function using the theorem. So the joint probability density function of y is, so here actually this vector is u, so this is u1 u2 is given by f of u is equal to absolute values of the Jacobian, then f of, so what was the random variable, this is f of x, so f of x, or we can write x1 x2, or let us, for simplified notation we are using f of x, so this is inverse of this y. So then this Jacobian is, we know that this Jacobian, this will be is equal to, so this Jacobian is nothing but u1 by root over u1 square minus u2 square. So u1 by root over u1 square minus u2 square. So let us write this is equal to u1 by root over u1 square minus u2 square, and then we have to find what is f of x1 x2. So because whenever we are transforming in this region, so for x1 x2, so here x1 is equal to, let us remember that what is x1, so x1 is transform root over u1 square minus, so x1 is root over of u1 square minus u2 square, and x2 is just x2 is nothing but u2, so then just hy is this inverse we have to put here, so 4 into x1 x2, this is u1 square minus u2 square into u2, 4 x1 x2, and e to the power of minus x1 square plus x2 square. So x1 square plus x2 square is root over x1 square plus x2 square is u1 square. So e to the power of minus u1 square, e to the power of minus u1 square. So this is this value whenever this is true, 0 less than, whenever 0 less than u2 less than u1 less than infinity. Otherwise this value will be 0 for any other value, 0 otherwise. So that is now if we can simplify these things, so this is cancelled. So then we will get 4 u1 u2, 4 u1 u2 e to the power of u1 square whenever 0 less than u2 less than u1 less than infinity, 0 otherwise. So note that it is very we can see that this u1 u2 are dependent each other in the range. So this will be dependent random variable. You can also check from the definition if you find the marginals. So we will find the marginal density, because it is the question that it is given in the question that find the marginal probability density function of u1. So now we will find the marginal probability density function of u1. So because we found the joint, so the marginal probability density function, the marginal probability density function of u1 is given by f of u1 u1. This is equal to, by definition, minus mu into plus infinity. If you integrate this u1 u2, just du2 we want to integrate. Now this is the actually this is the notation u1 u2 u1 u2. So now this is a non-zero whenever this condition satisfies. So now we want to find the range for u2. u2 is 0 to u1. This is for given any values of u1. u2 is, and also for u1 is any value, because u1 cannot be negative. That's why u1 for any values u1 between 0 to infinity. So f of u1 and this is this will be, because this range of u2 will be 0 to u1. For any other case this value will be 0 and 0 to u1, and then this is 4 u1 u2 e to the power of minus u1 square d of u2. So now if you do the integration, because it is with respect to u2, so 4 u1 e to the power of u1 square, it will be outside this integral, then this will be 0 to u2, then u2 du2. So so actually because okay, so this is sorry, this is 0 to u1, yeah, so that's why this is 0 to u1 u2. So now this is integration u square by 2. If you use the limit, this will be u1 square by 2. So this will be nothing but 4 u1 e to the power of u1 square, and then this is u1 square by 2, 2 and 2 cancelled. So this is equal to 2 u1 e to the power of minus u1 square. So 2 u1 e to the power of minus u1 square. So this is for whenever 0 between u1 between 0 to infinity. Now then for any other value this is 0. So we have to write finally the joint the marginal probability density function. So this is the marginal density function of u1. The marginal probability density function of u1 is equal to, basically we are interested to know x1 plus x2, okay, no, it is for the question was u1 is x1 root over of x1 square plus x2 square. So here root over of x1 square x2 square is given by f of u1 of u1. This is equal to, what finally we got 2 u1 e to the power of minus u1 square. Okay, so yeah, so just I want to check whether there is any mistake. I think, I hope it is correct actually. Yeah, so you are, okay, yeah, sorry. So basically 2 cancel, then this is u1, then u1 square, so this will be u1 cube. So 2 u1 cube e to the power of u1 square. So because it has to be density, so just I was thinking that so it has to be, if you do the integration, so this will be the integration would set to be 1 2 u1 cube e to the power of minus u1 square, 2 u1 cube e to the power of minus u1 square, whenever this is 0 less than u1 less than infinity, this is equal to 0 otherwise. So you can see that if this satisfies between 0, so this is the density function. Just I wanted to check that whether it is a, if your calculations are correct. Otherwise, just I was thinking, because if you do this integration f of u1 du1 minus into plus infinity, this should be equal to 1. So now it is non-zero between 0 to infinity, and this is u1 cube e to the power of u1 square du1. So now how we will say, so that this integration will be what is the value. So now we will take a transformation, because we know the gamma function. So we will take the transformation u1 square is equal to some z. So then 2 u1 d1, this is equal to dz, and this limit of z will be 0 to infinity. So this is 0 to infinity. Now it is u1 square is z e to the power of minus z, and then just I am writing in this way 2 u1. So this function we can write like u1 square d e to the power of u1 square, then 2 u1 d u1. So then the 2 u1 d1 is dz, u1 square is z e to the power of minus u1 square is z for simplicity. So this is will becoming z e to the power of minus z dz. So now this is nothing but 0 to infinity z 2 minus 1 e to the power of minus z dz. So what is this? This is nothing but gamma 2. So gamma 2 is nothing but 1 factorial, which is 1. So then it is a density function. So that just I was trying to see that, then I found that this was a mistake in computation, then this is the final value. So that's why we found that using this transformation concept in the theorem, we can found finally the marginal probability density function of u1. Also we found the joint probability density function of u1 and u2. Next, let us discuss some other example. Here it is given. So let x and y be two independent continuous random variables with probability density functions fxx and fyy respectively. So here it is given that x and y are two independent continuous random variable and their probability density function given. So because it is independent concept, so joint probability density function also we can find. Then the probability density function of u is equal to x plus y. So basically in the by this transformation also we can find, but here you can see that it is given the probability density function of u equal to x plus y is given by this formula. So let us write down this, then we will try to see how it is coming. So suppose let us write down this formula here. Let x and y be two continuous independent random variables with the probability density functions fxx and fyy respectively. So xy be two continuous random variables. So then the probability density function of u is equal to x plus y is given by, so f of u is equal to, so you can see that this expression is given here, f of u is fx b fy of u minus b dv. So this is fx integration minus infinity to plus infinity fx b f of y u minus b dv. So in mathematics this kind of operation it is known as convolution of two variables. So here two functions fx and fy2 function. This convolution, by convolution we can find the this probability density function of sum of two random variables. Let us see that how it is coming. So now since they are independent, since x and y are independent random variables, the joint probability density function of this vector of xy is given by f of xy, because it is independent, this is fxx, by definition it will be multiplication of their marginal probability density function for all xy belongs to R2. So that is the thing. Now we will take this transformation u is equal to x plus y. Now since we do not have any formula for, it is only one transformation R2 to R, we need the transformation for using the Bivariate theorem, we need the transformation that R2 to R2. So we need another function. Let us consider for very simply v is equal to x. So then in the real number it is x plus y and v is equal to x. From here we can get this inverse x is equal to v and y is equal to u minus x which is equal to u minus v. So we have this inverse. So so this is the transformation actually. U v is equal to g of xy, yeah. So xy u v is equal to g of xy, which is x plus y x, and then we get this inverse xy, this is equal to g inverse of u v, which is h of u v. This is nothing but x goes to v and y is u minus v. So this is the transformation. So because this transformation the inverse exists, now we have to check this Jacobian. So what will be the Jacobian? This Jacobian is given by definition. This is the determinant of this Jacobian we are writing by j. So this is because we are taking transformation u x, so del x, del u, del x, del v, then del y, del u, del y, del v. So then this transformation we found that, so what will be those values? So del x, because x is equal to v, so this is the component vector if you write. So this is h1 of u v, this is h2 of u v. So this is the h1 of u v, it is function of v only, and this is h2 of u v. So now del x del u will be 0 because it is independent of u, del x del v will be 1, and then del y del u. So del y del u is here, del y del u will be 1 and del y del v will be minus 1. So determinant will be minus 1 for any value, for all u and v belongs to R2. So now because then see that this is minus 1. Now hence the joint probability density function of u v, so of this vector u v is given by f of u v, this is equal to by the theorem, this is absolute values of the j, f of x y, and then the inverse actually h of u v. So then because this is 1, so then Jacobian is j is 1, and because f x of y is, so basically you can write f of x y h1 of u v component vector, and then it is h2 of u v. So now because it is independent, this will be is equal to fx of h1 of u v and then fy of, because independent from the independent here fxx, fyy, fy of h2 of u v. So now what is fx h1 of u v? h1 of u v is v, so this is fx v into h, then h2 of u v is u minus v. So then fy of u minus v. So this is the joint probability density function. So let us write down here. Hence the joint probability density function is found here. Hence the joint probability density function of u v is given by f of u v, this is equal to what we found, just I am writing again, this is here f of u v is fx v into fy of u minus v, fy of u minus v. Now whenever we know the joint probability density function, we can find the, because we are interested to know the u equal to x plus y. Now the marginal probability density function of u, which is nothing but x plus y, is given by, so because we know the joint, the marginal will be by definition minus mu into plus infinitive FUV UV dV. So this is equal to minus mu into plus infinitive. So FUV UV is Fxv and Fy of u minus v that we found with dV. So this is the theorem actually, you can see that this is the theorem, it is given here, the joint probability. So here you can see that. So f of x and y be two independent continuous random variable with probability density function fxx and fyy respectively. Then the probability density function of u is equal to x plus y is given by fu is equal to minus mu into plus infinity fxv fy of u minus v dv. So I hope this is we also found finally, fu of u is equal to minus v into plus infinity fxv fy of u minus v dv. So this is the theorem. I hope you have understood it. Otherwise you can go through again, so then it will be clear, and also we will discuss some example based on this theorem, also numerical example, some particular distribution of x and y we consider, and then we will try to find what is the distribution of u, how we can find that.